Thanks, Jeff. So I'm going to be speaking about work I've been doing over the past 2 years or so on making high-speed line rate switches programmable. This is joint work with a number of collaborators from several different institutions we've listed here. So to start off, this is what I consider sort of the traditional view of networking as probably taught in an undergrad class. It's almost this dogma of having fixed or simple switches and programmable or smart endpoints. So you see this reflected in most applications today, whether it's web browsing or video conferencing. The smarts are in the clients and the servers, and the switches themselves are just relegated to first order to just the task of forwarding packets. Now, over time, this view has started showing signs of age. Perhaps the simplest symptom of a problem is that switch features are tied to fairly long design cycles in hardware. So the fastest switches today are built out of dedicated silicon, which means even if you want to introduce what in my view is a fairly benign change, like a new protocol format, you need to wait 2 to 3 years to see that in the next generation of the switch. And at the same time, operators, especially within data centers, seem to need much more out of their switches for a variety of reasons. And finally, as a researcher, it's deeply frustrating that if you come up with a new switch algorithm, you can basically not deploy it in a production network today because there's no way of changing a switch to run a new algorithm. So ideally, the solution to these problems is to have a programmable switch where you can change the functionality on the fly instead of waiting for the next generation of switch hardware. So how have switches over time stacked up against this goal? So the early switches from the early days of the ARPANET through the mid-90s, and I've listed some of these here, they were built out of mini computers or server machines. So they were essentially servers that were branded as routers because they had some special purpose forwarding software. This approach was sufficient because the forwarding rates at the time were under a megabit per second. It was also eminently programmable. If you wanted a new switch, you just took out the forwarding software, replaced it with something new, and you got a new switch. Now, since the mid-90s, the situation has changed, partly because as the internet exploded, link speeds exploded as well. So this chart tracks aggregate single chip switching capacity since the late 90s. And on the red line here, I'm plotting the performance of the fastest hardware switches at those points in time. So this is what I mean by line rate for the rest of the talk. So I use that term to denote the highest speed supported by a particular wire standard like Ethernet. At the same time, there have been several attempts at software switches that use some programmable substrate. But hopefully, the implication here is clear that software switches, regardless of their substrate, end up losing 10 to 100x in performance. So the vision for much of my work is whether we can have the best of both worlds. Can we have the performance of the fastest fixed function switches that are built out of dedicated silicon today, but at the same time, make them much more programmable than the fixed function nature of these devices today? And I'm talking about programmability that far exceeds OpenFlow or software-defined networking. So OpenFlow allows you to program the control plane of the switch by moving it out of the switch and onto a server. It has little to say about programming the data plane behavior of the switch within the switching ASIC. At the same time, we concede that this programmability is a purpose-built for the domain of switching. So we're not looking at a Turing-complete software switch that allows you to do arbitrary kinds of packet processing. And that's a compromise that I view as reasonable because that's what you give up for retaining this high performance. So over the past 3 years or so, several chips have emerged around this paradigm. And the most recent of these chips have performance comparable to the fastest fixed function chips today. There are also languages such as P4 emerging to program these chips. So with that context, let me describe the internals of a switch so that I can then describe my own contributions within the context of a switch internal. Okay, so a switch has a pipeline. This pipeline starts off with a parser. The parser takes bytes coming off the wire, turns it into sort of a bag of header fields. This bag is passed through the pipeline on some kind of a bus. The pipeline is structured as a sequence of match action tables. So the match just filters out packets of interest such as TCP or UDP packets, the action carries out things like packet field manipulations, such as decrementing the TTL field. The packets then end up in the scheduler, where they just sit around till an output link is free to schedule a packet. There's a similar egress pipeline, and then packets are sent out. So within this, I'll talk about 3 concrete pieces of work. The first two have to do with the pipelines. The first third of the talk, I'll talk about a machine model that formalizes the computational capabilities of the ingress and egress pipelines. So what does it mean for these switches to be programmable? What does their instruction set look like? And what are the design considerations when designing these instruction sets? The second third, I'll talk about a high-level programming model for these switch pipelines. And this is in the same spirit that you don't want to program your x86 chip in assembly. You ideally want a high-level programming model for the x86 chip. And finally, I'll talk about how to program the switch scheduler, which is the part of the switch that decides which packet to send out next when an output link is free.
By the way, this screen behind you actually has your full slide on it, in case you see the bottom. Yeah.
Okay, so let's look at the machine model. So as I said, a switch is a pipeline of match action tables. The match just serves to filter out packets of interest. The actual packet processing happens in the action. So let's just focus on that. These action units might have access to some local state. This could be as simple as a counter that counts packets going through the data plane of a switch. It could be more involved, like we'll see in this talk. When packets go through one stage of the pipeline, the action units operate on different slices of the packet in parallel and transform them sort of in lockstep synchronously, and then send them off to the next stage. So in steady state, you can assume packets going through this pipeline one after the other. The animation's a little slow, but the more important thing here is the typical requirement for one of these pipeline stages is the ability to process a packet every nanosecond, right? So you're looking at a clock rate of about 1 gigahertz for typical switching pipelines today. Okay, so this combination of the state plus the action unit that operates on the state, we call it an atom. And we use this to denote the smallest unit of atomic packet processing that the hardware exposes as an instruction to the compiler and to the programmer. So what does an atom look like? Here's an example atom. Here we take a piece of state X and either add or multiply a constant based on a choice control variable that sets the output of a mux. So this is an example atom. And you can imagine coming up with different kinds of atoms and specifying how many stages you have in the pipeline depth, and how many atoms you have within each stage, the pipeline width. And with these pieces of information, you've essentially encoded the switch's instruction set. So that's the machine model for the switch. Now, let's look at some design differences between atoms that do and do not manipulate state within the data plane of the switch.
So,
yeah.
Is this the definition of a finite state machine, basically? Is it just a combination of hard and some state? Is that what we define as an or is it more specific?
Well, in theory, yes, you can take state and run like an arbitrary function on it and update the state. But in practice, in order to meet the timing requirements of processing a packet every nanosecond, the amount of computation that you can carry out is limited to what you can finish within a nanosecond in hardware.
So, so you have some specific operations in mind? When
yes, we'll get to those. Okay. So let's distinguish between atoms that do and do not manipulate state, because I think it's useful to understand this, to understand how these atoms need to be designed. So let's say we have this stateless operation that takes a pair of packet fields, subtracts a third, and writes it into a fourth. Now, how do you do this in hardware? You can imagine a two-stage pipeline, which will take a bit longer to render. But the first stage of this pipeline takes the fields F1 and F2 and writes it into a temporary field that you've told the parser to reserve some space for. The second stage of the pipeline subtracts F3 from temp and writes it into F4. Now what I did here was to take an expression involving 3 packet fields and break it down into a sequence of pairwise operations on pairs of packet fields. But this is more generally true. You can take a more complicated expression and sort of whittle it down into these pairwise operations on pairs of packet fields. Now, as a switch designer, this makes life very simple when you're trying to design these stateless instructions. You can basically provision for all binary operations on a pair of packet fields and then use the compiler to do exactly what I just did. The consequence is it's straightforward to pipeline these stateless operations because each packet is completely independent of the next. So let's see if we can apply the same trick to a stateful operation. So here's the simplest example I could think of, a counter. And here's an attempt at pipelining it. So you have a piece of state X that is read in one atom into a temporary field. The second atom increments that temporary, the third one writes it back. Now, would this approach work? Let's say you have 2 packets, red and green, arriving back to back at clock cycle 0 and 1. So red just shows up now. After clock cycle 1, red's temp has picked up 0, green has just entered. After clock cycle 2, green's temp picks up 0, which is the old value of X. You can probably see where this is going. As green makes its way through the pipeline, it gets incremented to 1, and it ends up writing 1 back into X. So after 2 packets have gone through the pipeline, X is now still 1, when in fact it should be 2. So the problem with this is you're taking the stateful operation and you're trying to pipeline it into a sequence of stateful atomic instructions, and that doesn't quite work. Instead, you need to provide an atomic instruction that implements X++ so that the next packet arriving at that atom sees the updated value of state. And this is more generally true. If you have like an abstract operation where you take a piece of state S, apply some functionality on S, and write it back into S, you need to actually provide an atomic instruction that corresponds directly to this operation, because there's no easy way to take this operation and pipeline it into a sequence of smaller atomic instructions. And as a result, the stateful operations end up looking, the stateful operations and hence the stateful instructions end up looking far more complicated than garden variety x86 or ARM instructions, as we'll see in this talk. Okay, so that is the machine model of the switch, and hopefully it gives you a sense for the kinds of programmability that are enabled at the hardware level. But how do we exploit this? What's a good model for programming the switch pipeline? So our abstraction for that is something we call a packet transaction, which is a block of imperative code that captures an algorithm's logic. And we use the term transaction here to refer to the fact that this block is atomic and isolated from other instances of this block. Formally, the semantics of a transaction are very straightforward. A packet comes in, you execute a sequence of statements within the transactions block. You execute the sequence sort of sequentially. You end up updating some packet fields and some state in the process. And only after you finish this packet do you move on to the next packet. So the programmer's view is that you're processing one packet after another serially with no overlap in processing across packets. So here's an example. This is an algorithm that samples every 10th packet by counting from 0 through 9 and sampling the 10th packet. So let's say you get P1. At the end of P1, count is incremented to 1, but it's not sampled. With P2, you have a similar story, but notice that we're processing P2 only after P1 is completed. And we keep going serially until we get P10, which then is actually sampled because count is at 9. So this sort of gives you this illusion of processing packets serially on almost an extremely fast single-core processor without having to worry about underlying hardware details like pipelining and what atoms are actually available in the hardware. So we applied this abstraction more generally to a whole host of networking algorithms that span things like measurement, congestion control, load balancing, and so on. And I've listed out the number of lines of code when expressing these as packet transactions. And the number of lines of code is actually not too different from how many lines you would write if you were to express these algorithms as pseudocode or as code for a software switch. So that should give you some sense for the fact that these transactions are a fairly expressive abstraction for the kinds of algorithms we care about. Okay. By contrast, if you were writing one of these algorithms in P4, which is the status quo for switches today, you would have to deal with concurrency head on. You would actually have to say what happens in every pipeline stage. And much of the work of the compiler for packet transactions is to automate this process, as we'll see. Okay, so how do we compile these transactions? The programmer supplies a transaction written in an imperative language that we call Domino. This is similar to C or Python, except we forbid loops of any kind because there is no clear way to synthesize a loop with an unbounded iteration count and still guarantee line rate performance. We feed this to a compiler that does two main things. It extracts out these code fragments that we call codelets. And if we run those codelets atomically, you can guarantee the semantics of the transaction that I just described. And in the second step of the compiler, we take these codelets and map them to underlying atoms provided in the hardware. Now, it might turn out that the space of computations that the atoms capture because of their digital circuitry is insufficient to actually implement the codelets, in which case we reject the code and tell the programmer that it can't be mapped. Now, this is a rather different trade-off from programming on a software switch. On a software switch, all code that you throw will be compiled, and the performance will depend on how complex the code is. On a line rate switch, all code that compiles will run at line rate, but there will be code that is rejected by the compiler because conservatively it doesn't know how to actually map it to the hardware to run it at line rate. Okay, so let's go over the compiler in a little detail. So the first step is to go from this serial view of the code that the programmer supplies to this pipelined codelet representation that is closer to the hardware. So this is the same packet sampling code, except it's being pre-processed in a few ways to make it more amenable to compiler analysis. So we start with one node for each instruction in the transaction. We add dependencies between these nodes to reflect dependencies within a packet. So for instance, while processing the current packet, packet.old is written in the first node and then read in the second node. So there's a forward arrow in that direction. But the more interesting thing is dependencies across packets. And this is captured through state maintained on the switch, for instance, count. And we represent these dependencies by pairing up every read and write to a piece of state. So the intuition for this is you want the write to a piece of state for this packet to complete before you read that state for the next packet. Otherwise, you don't have the correct value. You also want the read to a piece of state to finish before you modify and subsequently write the state for any given packet. So that's the intuition between those two arrows, the two red arrows. So at this point, you look for strongly connected components in this graph. And these strongly connected components are the codelets that you're looking for. So the compiler's sort of correctness theorem is that if one of these strongly connected components, which is also a codelet, is run atomically or can be run atomically by the underlying hardware, then you can run that transaction with the semantics that we have at line rate. Okay, so now that we have the strongly connected components, we fuse together all nodes within a component and only retain nodes across components. And this gives us a DAG with our codelets. So we've taken out all edges within a component. And we can now sort of just schedule this DAG into a pipeline by just doing a topological sort. And at this point, we have this codelet pipeline that we're looking for. So if you take the code, as you can see it right now, if there were any way to run any of these codelets, all of these codelets atomically on the given hardware, then you can run this algorithm. So the second step of the compiler checks that. So it takes these codelets, looks at the underlying hardware substrate, and maps the codelets one by one to atoms provided by the underlying hardware. So we do a rather simple heuristic for this now. We just assign each codelet independently to an atom. There's no kind of packing of codelets into atoms. And we also assume the substrate is homogeneous. There's a single atom type that is tiled through the whole fabric. And in the process, if you run out of either pipeline depth or width, you just reject the code. But assuming you've gotten past that process and you do have enough atoms, you still haven't checked if the codelet can actually be implemented by the circuitry within the atom. So I'll give you an example of what I mean by checking this process. So let's say you had this atom, which is the same one from earlier, where you add or multiply a constant into a state variable x. If you have supplied the codelet x equal to x plus 1, you can map it to this atom simply by setting constant to 1 and choice to add. If, on the other hand, you supplied the codelet x equal to x times x, there's no way to map it to a single instance of this atom, because there's no setting of constant and choice for which these two are equal. Right? Concretely, we used program synthesis to solve this problem, where we're trying to synthesize the right configuration settings for the atom that makes it implement a specification, which is the codelet. But popping up one level, this really is the crux of the compiler. It tells us if the algorithm that was supplied by the programmer can or cannot run at line rate. So it can be rejected for one of two reasons. Either you ran out of pipeline depth or width, or this part of the compiler wasn't able to map your codelet to any of the computations available within the atom. Okay. So there's obviously one immediate use case for a compiler, which is, once you've built a programmable switch, you take programs and compile it down to the switch. But I think a more interesting use case is when you're designing these programmable switches in the first place. So can you use it as a tool to run these thought experiments where you say, if I had these instructions, what algorithms could I support? And can you iteratively refine the instructions in the process? So here's a blueprint of how that would work. You supply an algorithm written in our imperative language that we call Domino. We supply a specification of the atom that tells you what the input-output behavior is. We specify the pipeline geometry, which is the depth in terms of the number of stages of the pipeline, and the width in terms of the number of atoms per stage. We feed all of these to a compiler, which tells you if the algorithm compiles or not. Okay? So invariably, when you start out, the algorithm doesn't compile because the atom that you're trying out is too simple. And then you iterate by either increasing the number of atoms in terms of depth or width, or just changing the circuitry within the atom to capture more computations. Either way, you iterate until eventually the algorithm does compile. At this point, you move on to another algorithm, and you sort of repeat the process till you're satisfied that the atom covers as many algorithms that you care about, right? Okay, so let me show you a demo of this in action, because I think that'll explain this a little better. So we need to start out with some algorithm, and this should also give you a sense for how we program in Domino. So this is an algorithm that we call a learning filter that learns pairs of source port, destination port in the data plane as packets go by, and it uses a Bloom filter underneath to do this. So it maintains, okay. So it maintains these three pieces of states. state, filter 1, filter 2, and filter 3 that correspond to 3 ways in a Bloom filter. So that's the state that is persisted in the switch across packets. This line here is the signature of the packet transaction, which just takes a packet as an argument and implicitly all the state that is available globally. So the body of the transaction does the following things. It computes 3 indices into these 3 different arrays using 3 independent hash functions. Because it's a Bloom filter, it checks membership at all those locations. And because we're trying to learn new pairs of ports in the data plane, you set the membership bits at those locations as well. Okay? So this is the algorithm. We need an atom to go along with this because you need some atom pipeline to sort of bootstrap this process. So the simplest atom that I could think of is something called the read-write atom. This atom allows you to either read the latest value of a piece of state in the data plane and write it into a packet field on every packet. It also allows you to write either a constant or a packet field into a piece of state X, right? So that's the functionality that's provided by this atom. So let's see if we can compile the learn filter algorithm to a pipeline made up of these read-write atoms. So when we run the compiler, we supply the algorithm, a file format that describes the input-output behavior of the read-write atom, and a pipeline depth and width. We start out with a pipeline depth and width of 2 because that seems like the natural place to start. So this takes a while and just tells you that it cannot find a mapping because the pipeline is too small and you need a larger pipeline for this piece of code to compile. So let's increase the pipeline to about 10 in both dimensions. And now when you run this, it takes a little longer and it actually finds a mapping and tells you what the pipeline configuration looks like. So it tells you in each pipeline stage what are sort of the active atoms which implement this algorithm. Okay, so let's move on to a slightly more complicated algorithm. This is something that I call a heavy hitter detector. This is a fairly well-known algorithm for detecting flows with large traffic volumes in the data plane. And underneath it uses this probabilistic data structure called a countment sketch that counts flow volumes. The state here is similar to the Bloom filter state. There are 3 arrays representing 3 rows in a countment sketch. You again hash into those 3 locations, so that's similar as well. This is the piece of logic that detects a heavy hitter if all 3 locations exceed a particular threshold. And because you're counting packets in the data plane, we increment those locations within the countment sketch, right? So again, hopefully these 2 algorithms give you a sense of how to program in Domino. It's not very different from how you would write algorithms for a network simulator or a software switch. Okay, now let's see if the compiler can compile the heavy hitters algorithm to a pipeline of the same read-write atoms from before. So it takes a while, and this time it fails to find a mapping because it says the atom isn't expressive enough. And if you look at the heavy hitters algorithm, this should make sense because the stateful manipulation within, okay, there's a bit of lag, okay. The stateful manipulation within the heavy hitter detector is this ability to read a particular location in an array, add one and write it back, while the read-write atom only allows you to write a completely new constant or a new packet field into a piece of state. It doesn't allow you to use the old value of state, add something, and write it back. So this makes sense. So can we move on to a slightly more complicated atom so that heavy hitters can actually run at line rate? So the next most complicated atom that I could think of is something called the read-add-write atom that takes a piece of state X and adds either a constant or a packet field to X and writes it back into X, right? Now, by setting the constant to 1, you would imagine that the heavy hitter detector would be able to run on a pipeline of these atoms. So let's see if the compiler tells us that. So we run the same command line as before, but with read, add, write. Now it takes a while, and it finds a mapping, and again prints out the pipeline configuration. Okay. So hopefully this should give you a sense of how you can use this compiler to sort of create a new atom and then check your work and see if an algorithm actually compiles to this atom that you came up with. So we in fact went through this whole process and designed an entire hierarchy of such atoms. The first 2 atoms are the same atoms that I showed in the demo. The interesting thing about the hierarchy is that every atom on this list can express all the computations that its predecessors can. And the reason we went with this approach was because we were sort of looking for this one atom that could subsume all computations that we could then sort of declare as the atom that you should be implementing on a programmable switch. You could imagine a different approach where different sets of atoms provide different kinds of stateful update functionality, and you have a switch substrate that's made up of multiple kinds of atoms. Okay, so now that we have the atoms, let's actually go through what a network operator would do when compiling these packet transactions to switches made up of these atoms. So these are the same algorithms from before, and we take each of these algorithms and compile it to a pipeline of each of those atoms, so sort of the full Cartesian product. And here I've listed the most expressive stateful atom required from the underlying hardware in order for the algorithm to actually run at line rate. Again, the first 2 entries here should be clear from the demo. The Bloom filter just needs a read write for test and set. The heavy hitter detector needs you to read, add, and write back. But the more interesting thing here is the Codelets algorithm that doesn't map, because internally it has the square root operation on a piece of state that is more than any of our algorithms can provide. Now you could fix this by having a lookup table that approximates square root, but the broader point still remains that no matter what atoms you come up with, there will be some algorithms that are rejected because they cannot be run at line rate because the space of computations is finite within an atom. How many atom instances did we need? So this is the pipeline depth and width for each of these algorithms. And if you put them together, around 100 atom instances suffice. Now, how much do these atom instances cost in hardware? We wrote these atoms as circuits in Verilog and synthesized them to a recent transistor library, and they all meet timing at 1 gigahertz with considerable slack. So it's actually not too hard to build these out as hardware circuits. Furthermore, their area overhead relative to a baseline switching chip is quite modest. So here are some concrete area numbers.
I warned you. Yeah.
Okay. So as you can see that the area overheads are actually pretty small even for the most complicated of these atoms, and the areas increase as you go down the hierarchy, right? And that's to be expected because the atoms get more complex. Well, the takeaway here is it's less than about 1% additional area for 100 atom instances. Now, obviously this number depends on the number of atom instances. And obviously at some point you might pack so much functionality into an atom that it starts violating timing at 1 gigahertz, at which point you might have to come up with multiple different kinds of atoms, each of which meets timing at 1 gigahertz but provides you different sorts of functionality. But the point I'm trying to impress upon you here is that it's actually quite a small amount of additional area, and it's actually feasible to do many of these stateful computations at a clock rate of 1 gigahertz.
So what about the wires area for connecting these atoms?
Yeah, so we have a slightly more nuanced analysis that includes the cost of the muxes that take outputs coming from one stage and going to the next stage. that adds another % or so. Again, the cost of the muxes itself keeps going down because that's just combinational circuit.
Yeah, but the wires connecting them might be.
The wires, in some sense, is cost that you need to pay even for a fixed function switch, because you need to shuttle the packet headers from one stage to the next. So that's not something that you additionally add for a programmable switch.
Unless you had to add another stage just to make the number of atoms work out, right?
Yes, if you need to add additional stages, yes, that is additional cost. If you wanted to widen the number of your headers, because it's a programmable switch and you want 100 headers, then you would have to add this. But for most of these algorithms, we don't need too many headers. In fact, the ones that stress the number of headers are, I guess, these things like the tunneling formats, which then have internal headers and so on. So these are the ones that stress those dimensions.
And can you do the tunneling just by recirculating, or is that?
No, I mean, for tunneling, there are sort of switch primitives that allow you to add and remove a header at each stage.
And I assume that the area would be quadratic with the number of atoms, or isn't it? You are assuming that it's linear, right?
The area, yeah, right now we've taken an individual atom's area and multiplied it by the number of atoms.
Right, but that's why I'm bringing in the wires, because it might not scale linearly if you're trying to connect all of them to
we don't have a full mesh across these 100 atoms. These 100 atoms are spread out across the pipeline stages.
But in the previous slide you had the width as well, that they need to communicate within the pipeline stage.
So you're saying it's quadratic with the width within a particular stage?
Yeah, the multiplexer is obviously, it has to pay those many wires within the width of a pipeline stage, but you're not going to have 100 atoms within a pipeline stage. You're going to have 100 spread out over, like, say, 10 stages and 10 atoms per stage. Okay. So that concludes my discussion of the ingress and egress pipelines. Now, in the last part of the talk, I'll talk about the switch scheduler, which is the part of the switch that transmits packets whenever a link is ready to schedule something. And so far, if you look at switches, the schedulers on them are fairly limited. These are things like round robin, priorities, and traffic shaping. And you can change the coefficients in these algorithms, set a few configuration settings, but can't change the underlying algorithmic logic itself. So why is this? Why has programmable scheduling been so hard? I contend that it's not for a lack of algorithms. We have enough scheduling algorithms, but there's little consensus on the right abstractions that underlie all these scheduling algorithms. This is in contrast to other aspects of the switch pipeline that have become programmable, such as parse graphs for parsing and match action tables for forwarding. And this lack of an abstraction has a real consequence, especially because the scheduler has fairly tight timing constraints of 1 NQ and DQ every nanosecond. So you can't just get rid of any abstractions altogether and just throw a CPU in the fast path. It just doesn't cut it for the kinds of performance numbers we're targeting. So in summary, what you need is an expressive abstraction that can actually run at line rate, where by line rate, I mean a 1 gigahertz processing pipeline. Okay, so to get at this abstraction, let's start at the beginning. What does the scheduler do? It decides on two things: the order in which packets are sent for work-conserving algorithms like first come, first serve and priorities, the time at which packets are sent for non-work-conserving algorithms. Now, these aren't mutually exclusive. You could put them together to come up with more exotic combinations, but any programmable scheduler needs to provide flexibility on these two attributes. So here's a strawman programmable scheduler that in some ways reflects the way scheduling is done on fixed function switches today. So packets come in, they're classified into one of a number of first in, first out queues, or per flow queues. And then there's some programmable logic that tells you this flow goes next, or hey, it's time for this flow to send according to its token bucket. Now I should send this flow. Now, this is pretty similar to how even fixed function schedulers are implemented today. The scheduling logic runs on the DQ side and sort of goes round robin across ports and then arbitrates within queues within each port. So can we just extend that and make that piece of hardware logic programmable? So it turns out the problem with this approach is that there's actually very little time on the DQ side. So if you're going to be DQing a packet for a 100G or a 400G link, you have less than a few nanoseconds, like about 5 clock cycles at the lowest packet size, to DQ packets before you have to DQ the next packet. Now, this limited time is a problem because these scheduling algorithms aren't pieces of computation that can be easily pipelined because they have considerable amount of state, and the presence of state complicates pipelining, like I outlined earlier. Now, the net result of all this is if you were to do programmable scheduling on the DQ side, then you're really limited to those 5 clock cycles, and there's only so much programmability you can pack into 5 clock cycles, right? So the question that we're trying to go after is, can we move the programmability to the NQ side so that you potentially have all the time in the world from when the packet was transmitted at the end host to when it's received at the switch scheduler? So our abstraction for scheduling does exactly that. And the sort of new insight that we have here is that in many schedulers, the relative order of buffered packets does not change once packets are actually in the system. So what do I mean by that? When a packet comes in, you can determine its rightful place in the scheduling order as it's enqueued. And you can just leave it there, secure in the knowledge that you don't have to move around packets related to other packets that are already in the buffer. So a natural primitive for this is something called a push in first out queue, where packets are pushed into an arbitrary position based on a rank, but DQ'd from the head. Now this rank could either reflect the scheduling order or scheduling time. And this is essentially a priority queue. We use the term PIFO because it captures both the work conserving and non-work conserving use cases, while a priority queue is typically just used to implement strict priority work conserving scheduling. So this is a mock-up of how it works. Let's say you got a packet with rank 8. It gets dropped between 7 and 9. And as you can see, you don't have to move around the remaining packets related to each other. You have to move them one index to make room for the new packet, but 7, 5, and 2 don't get reordered related to each other. So how do we build a programmable scheduler on top of a PIFO? Really, the only thing that you can program in the scheduler is the way the ranks themselves are computed. The part of pushing a packet into a particular location based on the rank and generally just keeping the array sorted by rank is not programmable in any sense. It's just fixed. And what do I mean by programming the rank computation? You can write out any sequence of steps that eventually sets a packet.rank field. So this is something I just made up, where you take a packet's flow, look it up in a lookup table called T, and for whatever reason, add T.length to it, and that becomes the packet's rank. Now this is really the key modularity in the design. There's the fixed logic, which just does rank enforcement, and there's the programmable logic that actually does rank computations. And note that we've now moved all the programmable logic onto the NQ side. And we are giving up something. It only satisfies algorithms for which you can actually determine a packet's scheduling order on the NQ side, but this class is broad enough. And by moving it to the NQ side, we have a much larger time budget to play around with. So concretely, where do these two paths go within a switch? The PIFOs replace the standard queues, while the rank computation runs on the ingress pipeline. And we can repurpose the packet transactions machinery to actually run the rank computation itself. So here are a couple of examples. So the well-known fair queuing algorithm is one. So we use the virtual start time fair queuing implementation here, where for every packet, we track its virtual start time relative to an idealized fluid fair queuing system. And that becomes the packet's rank in the PIFO. As a non-work conserving algorithm, we have token bucket shaping, which maintains a count of tokens that are incrementing at a certain rate and capped to a certain burst size. We set the packet send time to either the current time or whatever time in the future it would have made up the shortfall in tokens according to the token bucket. And this send time, the absolute wall clock send time, as opposed to the scheduling order, becomes the packet's rank in the PIFO. So these are both examples of rank computations running on the same switch itself, but we can also have the rank computation run elsewhere in the network. So let's take the switch pipeline and compress it down onto the switch and add an additional end host. Okay. And we can use this to implement shortest remaining flow size. So for every packet, we track its flow and we set the packet's rank to the remaining flow size in an RPC kind of system where you've sent some bytes, but you still have a few more bytes left within an RPC. Okay. So all of these examples illustrate what you can do with a single PIFO, and common to them is this property that packets that are already in the system don't need to be reordered related to each other. Now, there are practically important schedulers that violate this property, and the simplest of them is hierarchical schedulers. And the canonical hierarchical scheduler is hierarchical packet fair queuing. So HPFQ divides link capacity between two classes in some ratio, and then recursively within flows within each class. Right? And here are some example weights. Now it can be shown that if you try and implement HPFQ, you can't do it with a single priority queue or a PIFO because it requires you to reorder packets that are already buffered when new packets come in. But it also turns out we can implement these schedulers using a hierarchy of PIFOs, which is more than one PIFO. And this hierarchy is actually quite natural. It's somewhat isomorphic to the HPFQ tree itself. So the root of the hierarchy is a PIFO that schedules across two child PIFOs, red and blue. So this is a change in semantics. Now, instead of just scheduling across packets, we're scheduling across other PIFOs, sort of recursively. And each of the child PIFOs schedules across packets, just like before. Now, on the NQ side, let's say A1 showed up. Just the class for A is enqueued into the PIFO root, while the packet for A goes into PIFO red, right? And as you can see, at the root level, red and blue alternate because the ratios are equal. At the leaf level, A is ahead of all packets from B because A has a much higher weight than B at the leaf level. So that's on the NQ side. On the DQ side, you first start dequeuing from the root PIFO, and that pulls out B. Now, B is not yet a packet, but it's a pointer to another PIFO. So you chase that pointer, go to PIFO blue, pull out X1, and then transmit that. So the DQ process now involves traversing a chain of these pointers before you can DQ a packet. So that should have hopefully given you a sense that PIFOs are expressive, but are they actually feasible in hardware? To answer this, we set out to meet some performance targets that are typical for a shared memory switch. So the important thing here is the buffer is shared across all ports, and so is the scheduling logic. So any area numbers that we report for the scheduler don't need to be further multiplied by the number of ports. So what's the naive solution to this? If you had 60,000 packets that you wanted to support a PIFO over, the really naive solution is to have one array with 60,000 packets. And when a packet comes in, you compare it in parallel to all 60,000 elements and use these comparisons to determine exactly where the packet goes in, shift the array accordingly, and drop the packet there. Now, as you can imagine, having these 60,000 parallel comparisons is a non-starter. We need something more scalable. Yeah, I saw the time. Yeah, you need something more scalable for this to actually work in hardware. So we exploit the observation that most practical schedulers schedule across flows, implicitly using the observation that ranks increase monotonically within a flow. So how do we use that? Our hardware design has two parts. There's a flow scheduler that schedules across the head packets of all flows. And then there's a rank store that stores packets from the second rank onwards. Now on the NQ side, let's say you got rank 6 from flow C. That just gets stuck at the back of the rank store. If D4 shows up, there's no entry in the rank store. It goes all the way to the flow scheduler. On the DQ side, if you were to transmit a packet right now, you would send out A0. Then you would go into the rank store, pull out A2, compare it in parallel to all elements in the flow scheduler array, and drop it in the right location. Now, as you can see, we're still doing this parallel comparison followed by insert, right? Only now, the element A2 needs to only be compared against all head elements of all flows, which is about 1,000 elements, as opposed to the naive design where you have to compare it against all 60,000 packets in the buffer. So this is what makes this work. So we looked at the hardware feasibility of the design, and we first note that the rank store is just a bank of first in, first out queues. Switch designers commonly use this to buffer payloads. So we add it in our area calculations, but we don't actually implement the design ourselves. So the flow scheduler is a new part. So we wrote this as a Verilog circuit, and we're able to synthesize it to a recent transistor library and show that it meets timing at a gigahertz. So the limit of this design right now is about 2048 flows. It fails timing at about 4096. Yeah.
That's for a 10 gigabit switch. If you went up to a 100 gigabit switch or a 40 gigabit switch, would you end up having to handle fewer flows or?
No. So this is for a pipeline that has a 1 billion packet per second aggregate capacity. It's not dependent on whether that is divided up as 64 10G ports or 600G ports.
All right, so you might have to go to a smaller switch radix as you go up in actual line rate in order to make this meet timing. Okay.
Yeah, because it's provisioned for a given packet processing rate.
Right, okay. So if the packet processing rate went from 1 gigahertz to some higher number, you would presumably also have more trouble meeting timing.
So that's exactly right. But typically, people don't clock their pipelines more than a gigahertz. They have multiple parallel pipelines.
Right.
And we don't yet handle the case of multiple parallel pipelines.
Because you'd have to do some flow classification at the entry to those pipelines, and you don't know how to do it. Yeah.
No, the harder problem is actually we have this end-to-one pattern where you have packets being enqueued from multiple pipelines into an output port, which really requires you to deal with multiple NQs per clock cycle as opposed to just one NQ per clock cycle. So the flow classification itself at some level can be run in parallel in each of the pipelines. It's more this incast kind of pattern. Okay, so as an example of the area overhead, this takes up about 7 mm squared in this 16 nanometer node. And in return, you get a 5-level programmable hierarchical scheduler. And this is about 4% relative to a baseline switching chip. So to conclude, I'd like to distill a blueprint for programmable switches that at least I learned from both of these projects. And hopefully by now, you're convinced that high-performance networking needs specialized hardware where you purpose-build your silicon for the purpose of switching. But the specialization is at odds with programmability. On the one hand, you want to specialize enough to get really, really high performance out of your hardware and a limited budget of transistors. But if you specialize too much and go too far with this, you risk the hardware becoming obsolete the next year when your requirements inevitably change. So my view of resolving this tension is to tailor these programming abstractions to rather restricted classes of switch functions. So the restriction is what allows you to retain high performance because you're not trying to do everything that a Turing-complete CPU can do. And hopefully you pick important enough classes of switch functions so that your abstractions are future-proof in the sense that they cover current and future algorithms within that class. So this talk really was 2 examples of this approach for stateful header processing and scheduling. And in both of these cases, the abstractions are tailor-made to these specific classes of switch functionality. So it's far from a Turing-complete CPU. You can't use the scheduler to I don't know, run a matrix multiplication, for instance. We're applying a similar approach to designing high performance abstractions and primitives for measurement that will appear at hotnets. Software corresponding to these projects and papers are available at these links. Thank you so much for your time.
So before we take questions, just a plug. We have some time this afternoon, I think after 2, if anybody wants to meet one-on-one with Anirudh. And also, I think there's only a few of us going for lunch, so if you would like to join us instead in a couple minutes to go to lunch, lunch is on Google, it's free. So we have time for a few questions, including anybody who's left on the phone there. GBC, there are a few people left.
So what's the time target for the in-queue processing and the in-queue processing? What's the order of magnitude in the database?
So are you talking about the scheduler? Or?
Yeah, the scheduler.
Yeah, so you want to support, at the level of the entire switch, for a single pipeline switch, you want to support one NQ and one DQ every clock cycle. But for a specific port, even at the highest sort of speed of 100 gigabits per second, you want to support a DQ only once every 5 clock cycles, because you cannot run more than that on a 100G link. While on the NQ side, you could potentially get an NQ every clock cycle, even on a single 100G output port, because you can have this end-to-one kind of in-cast type scenarios transiently.
But there, the computation for that can be parallelized across all your pipeline. Each one of the packets is deriving once per clock cycle. Its rank computation can be done separately, and so you have more cycles per packet.
So that's an interesting question. So right now, all of this discussion is about a single pipeline switch.
Yeah.
If you have a multi-pipeline switch, and if you did not need to coordinate between state on different pipelines, then you could do them in parallel. Typically, many of these scheduling algorithms need you to maintain state that has to be shared.
Oh, I see. So you have synchronized in that state.
Yes, and that's not easy to do. So the multi-pipeline case certainly requires more work, both on the side of the PIFO and on the rank computation side. But yeah, if you can divide up state in a way that each set of packets needs its own access to some local state, doesn't need to synchronize with other pipelines, it should be still doable. Yeah.
I have a question. So how can we translate the same or extend this to the NIC use case? Because,
So I think that's a really good question. The problem is also a little easier with a NIC because you have 40G or 100G as opposed to 640 or a few terabits per second now.
multiple ports.
Yeah, so I think, in fact, if you use one of these programmable NICs, such as the ones Netronome sells, or I think even Mellanox has some of these at this point, I think the most straightforward way to go would be to take a PIFO and just implement it on like an FPGA attached to, like, say, a Mellanox NIC. Yeah, we haven't done that ourselves, but I think that's absolutely an interesting direction because that's actually much easier to do because you don't have to build it in like silicon. You can actually implement it on an FPGA or even a multi-core substrate.
Any last questions? Okay.
Yep.